effect may be defined. Photoelectric effect. Photoelectric effect may be defined as the phenomenon of ejection of electrons from the surface of a metal when light of suitable frequency strikes it. The electrons thus ejected are called photoelectrons. When light of particular frequency strikes the metal surface, electrons are ejected from the metal surfaces, which are detected by the detector. For a particular metal, there exists a threshold frequency such that at frequencies below the threshold, no electrons are emitted, no matter how large the intensity is or how long the radiation occurs. The number of photoelectrons emitted per second is directly proportional to the intensity of the incident radiation but does not depend upon its frequency. According to Einstein, electrons in metals are held by some attractive forces. To overcome these forces, certain minimum amount of energy is required, which is characteristic of the metal. This is called photoelectric work function W0. W0 is equal to h nu naught. Einstein equation can be written as h nu is equal to h nu naught plus Ke. Ke is equal to h nu minus h nu naught. Dual behavior of electromagnetic radiation. The photoelectric effect could be explained considering that radiations consist of small packets of energy called quanta. These packets of energy can be treated as particles. On the other hand, radiations exhibit phenomena of interference and diffraction, which indicates that they possess wave nature. So it may be concluded that radiations possess dual nature, that is, particle nature as well as wave nature. Assessment. Before evidence for the quantized electronic energy levels. Atomic spectra. The phenomenon of splitting of a beam of light into radiation of different frequencies after passing through the prism is called dispersion, and the pattern of radiations obtained after dispersion of beam is called spectrum. In case of dispersion of sunlight, the 7 colors obtained change from violet to red without any discontinuity, which means each color blends into the other. Such a spectrum is called continuous spectrum. Emission and absorption spectra. When an element is excited by some method, such as by heating, by passing electric current, or by passing electric discharge, the atoms of the element emit electromagnetic radiations of definite frequencies. The arrangement of these radiations in the order of increasing wavelength or decreasing frequencies is called emission spectrum of the element or atomic spectrum. Atomic spectrum of an element can be used to identify the element and is sometimes called fingerprint of its atoms. Atomic spectra of most of the elements consists of number of bright lines separated by dark bands. That is why atomic spectrum is also known as line spectrum. Absorption spectrum is the spectrum formed by the electromagnetic radiation that has passed through a medium in which radiation of certain frequencies is absorbed. Line spectrum of hydrogen. When an electric discharge is passed through hydrogen gas, its molecules dissociate into hydrogen atoms. The excited hydrogen atoms thus produced emit electromagnetic radiations of discrete frequencies. The spectrum obtained consists of a large number of sharp lines. Each line corresponds to a particular frequency of light emitted by hydrogen atoms. The lines in the emission spectrum of hydrogen are classified into 5 series as follows. Lyman series, it is in ultraviolet region. Balmer series, it is invisible region. Paschen series, Brackett series and Pferd series, these are in infrared region. The spectral lines are expressed in terms of wave numbers. Then the lines in the visible region obey the formula. Wave number is equal to 1,09,677 into 1 by 2 square minus 1 by n square per centimeter, where n is an integer equal to or greater than 3, that is n is equal to 3, 4, 5 and so on. After this, Rydberg gave a more general formula which is applicable to all the series in the hydrogen spectra. Wave number is equal to 109677 into 1 by n1 square minus 1 by n2 square per centimeter, where n1 and n2 are integers, such that n2 is greater than n1. For a particular series, n1 is constant. The value 109677 per centimeter is called Rydberg constant for hydrogen. Bohr's model for hydrogen atom. Bohr's model of atom is based upon quantum theory of radiations. Main points of this model are: the electrons in an atom revolve around the nucleus only in certain selected circular orbits. These orbits are associated with definite energies and are called energy shells or energy levels. These are numbered as 1, 2, 3, 4, etc. or designated as K, L, M, N, etc. shells. Only those orbits are permitted in which the angular momentum of the electron is a whole number, multiple of h by 2 pi, where h is Planck's constant, that is, angular momentum of the electron. mvr is equal to nh by 2 pi, where n is equal to 1, 2, 3, etc., where m is the mass of the electron, v is the velocity of the electron, and r is the radius of the orbit. In the other words, angular momentum of electron in an atom is quantized. As long as the electron remains in a particular orbit, it does not lose or gain energy. This means that energy of an electron in a particular orbit remains constant. That is why these orbits are also called stationary states. When energy from some external source is supplied to the electron, it may jump to some higher energy level by absorbing a definite amount of energy equal to the difference in the energy between the two energy levels. When the electron jumps back to the lower energy level, it radiates same amount of energy in the form of the photon of radiation. Delta E is equal to E2 minus E1 is equal to h nu. Nu is equal to E2 minus E1 by h, where nu is the frequency of the emitted radiation. Bohr's model for hydrogen atom. Quantization of energy and Bohr's model. According to the Bohr's model, energy of the electron in an atom is quantized. Quantization means that a quantity cannot vary continuously to have any arbitrary values, but can change only discontinuously to have some specific values. To illustrate this point, let us consider a simple example. Suppose a person moves down a staircase, then energy of the person changes discontinuously and he can have only certain definite values of energy corresponding to the energies of various steps. Energy of the person in this case is quantized. On the other hand, if the person moves down a ramp, then his energy changes continuously and he can have any value of energy corresponding to any point on the ramp. Energy in this case is not quantized. So, according to Bohr's model, energy of an electron in an atom is quantized. The main successes of Bohr's model are: Number 1. Bohr's model could explain the stability of an atom. Number 2. Bohr's theory helped in calculating energy of an electron in a particular orbit of hydrogen. The expression is En is equal to minus k square into 2 into pi square into m into e raised to the power 4 divided by n square into h square, where m is mass of the electron, e is charge on the electron, h is Planck's constant, k is Coulomb's law constant. On substituting the value of constants, we get En is equal to minus 1312 by n square kilojoule per mole. Bohr gives an expression for the radius of an orbit in hydrogen atom. Rn is equal to n square into h square divided by 4 into pi square into k into m into e square. Rn is equal to n square into 0.529 into 10 raised to minus 10 meter. Rn is equal to n square into 0.529 angstrom. Thus, as n increases, the radius of the orbit increases. The radius of first orbit of hydrogen